Everyone, all protocols duly observed. I am Festus from University of the West Indies. I'm here today to make a presentation on residual strength and post-cracking behavior of glass wool fiber reinforced concrete embedded with steel reinforcements. What is glass wool fiber reinforced concrete, GWFRC? Glass wool fiber reinforced concrete is a concrete consisting glass wool fiber bonded to a concrete matrix. That is, addition of glass wool fiber to plain concrete results in glass wool fiber reinforced concrete. Chiefly, cracking occurs when tensile stress exceeds tensile strength of concrete. From the image on top, concrete is being subjected to tensional forces which actually lead to some micro cracks in the concrete. But the presence of fibers in the concrete tend to limit the propagation of the micro cracks. Generally, fibers are known to generate a post-cracking residual tensile strength together with a large tensile strain by bridging. Thus, the load carrying capacity of the cracked concrete structure is the residual strength of that structure. Problem statements. Conventional concrete has certain undesirable attributes such as low tensile strength and cracks, especially in the tension region, as shown. These defects can largely affect the performance of concrete structures in terms of load carrying capacity and consequently shorten its expected service life. However, combining the excellent tensile properties of fiber and conventional steel bar in concrete is expected to improve concrete strength properties and as such result in concrete structure of an enhanced integrity. In this study, glass wool fiber, basically a waste material, and 10 mm steel reinforcement were used as reinforcing materials in concrete. Aim and objectives. The aim of the study was to investigate the residual strength and post-cracking behavior of glass wool fiber reinforced concrete embedded with steel reinforcement relative to conventional concrete as a construction material. Objectives are as follows: to determine the compressive and splitting tensile strength of glass wool fiber reinforced concrete cubes and cylinder specimens after 28 days of casting, of curing rather. To determine the residual strength, that is the 3-point bending of glass wool fiber reinforced concrete beam specimens with and without steel reinforcement after curing for 28 days. To attain and compare the strength properties, that is the compressive, splitting tensile, and residual strength of the tested specimens cast from plain concrete with those cast from glass wool fiber reinforced concrete. To assess the suitability or otherwise of combining glass wool fiber and steel reinforcement as reinforcing materials in concrete. Methodology. This includes specifications and selection of concrete mix, ratio 1:2:4, sourcing for materials, cement, fine aggregate, coarse aggregate, water, and glass wool fiber, casting of specimens, cubes, cylinders, and beams, specimen curing for 7 and 28 days, laboratory testing of specimens, and analysis of results. Analysis and results. Compressive strength of concrete cubes. The table shows the 4 mixes with their corresponding percentage glass wool fiber and the average compressive strength obtained in MPa. This is a bar chart of the compressive strength versus percentage glass wool fiber. From the bar chart, there was a 0.26% increase in compressive strength with 0.05% fiber and slight decline in strength with higher fiber content. Splitting tensile strength of cylinders. Also from the bar chart, there was a significant percentage increase of 20.83% in splitting tensile strength with 0.5% fiber content at 28 days. Then flexural and residual strength of concrete beams. Now the two tables shown, one for residual flexural strength, two tables show initial loading and reloading data without and with steel reinforcement. The peak load strength for the 3-point bending was actually calculated using 3PL all over 2 squared, where P is the peak load in newtons. All other parameters are in millimeters. In both cases, there was an increase in peak load strength with increasing fiber content up to 0.5% before a decline was observed. And the typical loading and reloading deflections curve for 0% glass wool fiber without steel reinforcement. The values in red, the values in red for the tables correspond to reloading curve, while the ones in blue is the initial loading curve. The two tables show average flexural residual strength data with and without steel reinforcement, and the ARL is the average of the reloading loads, the average reloading loads corresponding to 0.5, 0.75, 1, and 1.25 mm deflections read directly from reloading curves. Evidently, the average residual strength for both glass wool fiber reinforced concrete without and with steel reinforcement increased with increasing fiber content with optimal value 0.5% fiber dosage. And then these are the bar charts for the results. Now, conclusion and recommendation. In this study, the following conclusions are drawn. One, inclusion of glass wool fiber marginally improved the compressive strength of concrete. There is positive effect of glass wool fiber on concrete with increasing fiber up to an optimal content, beyond which a negative effect is experienced. The average residual strength for both glass wool fiber reinforced concrete with and without steel reinforcement increased with increasing fiber content with optimum value 0.5% fiber dosage. Recommendations. While working with glass wool fiber, safety precautions such as wearing of hand gloves and use of nose cover are strongly recommended. Moderate fiber burning fraction between 1% and 2% of glass wool fiber and other steel reinforcement diameters should be examined to fully investigate their effects on concrete residual strength. Lastly, combination of steel reinforcement and glass wool fiber in concrete should be encouraged in concrete industry, as their synergic tensile properties would have positive effects on the service life of concrete structures. And these are the references. Thank you.
Thank you. We have a few questions for you.
Okay.
First one, what is the reason for the reduction in residual strength and tensile strength for 1% fiber?
The reason for the reduction, basically, even from literature, it was obvious that by the time you put in your fibers, general fibers now, and not just glass wool. By the time you load up to 1%, you dose up to 1%, you start getting some reductions. And by the time you go above 1%, generally, fibers tend, the behavior, the performance tends to reduce. So, and then there's a previous work before this done on the strength only. And this already gave the range of this present work that has just been presented.
Okay. What was the aspect ratio of glass fiber?
Aspect ratio for this glass fiber was not determined. And the reason is this, it is a continuous fiber. It is a continuous, unless you deliberately break it. And that is why it is like wool. So if you, that's why we recommend, wearing gloves. So it's continuous, not like the crimped or the straight fibers for steel reinforcement. So it was not determined for this study.
Okay. Question, how was 28 days selected?
28 days after the molding, after casting. You cast today, then you start counting from tomorrow. You demold tomorrow, and then after 28 days, then you put inside water for curing. And then after 7 days, some batches were removed and tested. After 28 days, the final batches were removed and tested. Okay.
Other part of the question, did you look also at the variation of strength with the duration of curing? That is the variation of strength with days.
No, we did not look at that.
Okay, and they want to know is, even though your work is just experimental, will there be any attempt to predict the strength with fiber content and duration of cure mathematically?
No, but what we do know is that the concept of using fibers is actually not new. And a lot of work has been done on steel fibers. And when we are, preparing your blast resistant concrete, you need fibers. Those fibers actually make concrete more ductile. And that's the purpose. You make it more ductile, you bridge the gaps. You see, by the time you have concrete and you load concrete to its maximum point, there will be micro cracks. And the micro cracks will now tend to start the depreciation of that concrete. But when you use fibers, the fibers will bridge the cracks. So leading to an enhanced, structural strength and a longer life for that concrete.
Okay. Thank you, Dr. Olatuish. Professor Ray?
Okay, thank you, Dr. Alraj. It's a good presentation.
Yes,
Very good work.